Hello, I welcome you all in this course on refrigeration and air conditioning. Today is the last lecture of this course. We will take up some problem solving. Before that, I would like to discuss some troubleshooting issues in troubleshooting in air conditioning system. Normally, air conditioning system works between two pressure limits P1 and P2. Sometimes it is observed that this P1 starts increasing or P1 is higher than the rated value, because for air conditioning system it is always written the gauge pressure at this P1 is going to be this much, right. And if this gauge pressure is exceeding, or same is the case with the P2, P2 will also work at a certain gauge pressure. So, this P2 also gauge pressure is exceeding. What can be the probable reason? First reason is, probable reason is the system is overcharged. When system is overcharged, these pressures will shift, right, and you may not get proper cooling effect here, and here also the pressure will shoot. And this shooting of this pressure is not welcomed and it is not desired, because it has many side effects. It kills the lubrication system of the compressor, and ultimately some failure will take place inside the compressor. Another reason for this high pressure can be the presence of uncondensables. And or presence of air. If air is mixed with the refrigerant, saturation pressure of refrigerant plus the partial pressure of air will be the total pressure inside the system. So, I will give you an example. Suppose if you take refrigerant in a vessel, right, and it is a mixture of liquid and vapor, it is saturated vapor of refrigerant in a vessel at a room temperature, right. Now, it is mixed with the air also. So, what is going to happen in this cylinder? The stratification of air and refrigerant will be there. So, the moment you open the valve, air will come out. The moment air comes out, the pressure of this cylinder will fall. It means the pressure was there inside the system, because the moment the air comes out, the partial of the pressure of the air reduces, and that results in reduction in the total pressure. So, in the system also, if after in a calm system, if you purge some part of the purge from the top because air is lighter than refrigerant, right. So, if system is not running, stratification will take place and concentration of air in the top part of the system will be more. So, the moment the air is purged, the pressure will fall. If there is no air, if you are purging the system, boiling of liquid will take place and pressure will remain constant. So, that is how we can ensure that the system is without air. Second thing is overcharge, that is overcharge, uncondensables. Third thing can be that the water being circulated, cooling water temperature is high, if it is water cooled, or ambient temperature is high. In old days, when domestic refrigerators were used and the condenser was provided at the back side of the refrigerator, it was always recommended that at least 9 to 10 inch gap should be maintained between the refrigerator and the wall, so that there is a proper circulation of air. Even if in such a small machine, if you clean the condenser, just clean the dust provides considerable insulation effect. So, in a air cooled condenser, if you clean the condenser coils, make them free from dust, the cooling capacity of the system will increase. And here also, if it is overheated, if dust is removed, then pressure may reduce, if that is the reason, if dusting is the reason, or if the cooling water temperature is not appropriate. Why cooling water temperature is not appropriate? Because this cooling water, in what happens in a water cooled condenser, suppose there is a water cooled condenser, after picking heat in the condenser, the water goes to the cooling tower. cooling tower. You must have seen cooling towers outside the hotels and the buildings where air conditioned, which are centrally air conditioned. So this cooling tower is used for cooling the cooling water. So cooling water picks the heat in the condenser where the condensation of vapors takes place, and this in this cooling water, but cooling water has a, I mean normally when system is designed, it is assumed that the temperature drop in cooling water will be approximately 10 degrees centigrade. That is why the temperature rise in the cooling water in a condenser should not be more than 10 degrees centigrade. But for certain reason, this cooling water is not effective. Temperature reduction here is only 6 degrees centigrade. Maybe some outdoor conditions, because the performance of cooling tower is also dependent upon the outdoor conditions. Suppose outdoor air is humid, is already saturated, temperature drop will not be very high, but here the requirement is high. So slowly the temperature of cooling water keep on increasing, and that will shoot the pressure of refrigerant in the compressor. Now another case, the pressure in the evaporator is low. Pressure in the evaporator, certain gauge pressure has to be maintained in the evaporator. It can be vacuum also, in some of the cases it is vacuum also. So some gauge pressure, normally for example R134A, gauge pressure has to be maintained. It means the pressure inside the evaporator is higher than the surrounding pressure, and if this pressure is low, so what you are getting on a PV diagram, this is normal pressure, not yes, pressure enthalpy diagram, not PV diagram, pressure enthalpy diagram, state 1, 2, 3, 4. So if the pressure is going down, definitely the cooling capacity will reduce. So, and it is misleading, because here on the coils you will be getting temperature, suppose actual temperature is 5 degrees centigrade, in coil you will be getting minus 5 degrees centigrade, right. It is misleading. It appears that the cooling capacity has increased, though the temperature has reduced, reduced, but in this case cooling capacity has also reduced. So when the pressure is low in the evaporator, cooling capacity is also low, temperature is low and cooling capacity is also low, and this low temperature is normally due to undercharging of the system. It means the system is undercharged and it needs more refrigerant to be charged in the system. Now after these troubleshootings, we can take some of the typical problems of related with the refrigeration, like a simple saturation cycle of R134A designed to taking a load 15 TR. Refrigerator and ambient temperature are 0 and 40 degrees centigrade. Refrigerator and ambient temperature are 0 and 40 degrees centigrade. A minimum temperature difference of 10 degrees centigrade is required in condenser and evaporator for heat transfer. It means the cycle is not between 0 and 40. Cycle, this pH diagram, the refrigeration cycle is not operating between 0 and 40 degree. This is the outside temperature. So ambient temperature are 40 degrees centigrade. So temperature of so evaporator temperature is going to be how much? It is going to be minus 10. Sorry, evaporator temperature minus 10. And what about the condenser? Ambient temperature is 40 degrees centigrade. It means the temperature in the condenser will be 50 degrees centigrade. Refrigerant will condense at because at 50 degrees centigrade it will be dissipating heat at 40 degrees centigrade. Outside temperature is 40 degrees centigrade, and you can use the formula Q is equal to UA LMTD, right. So this is how we get the value of area of the condenser. So normally 10 to 15 degrees centigrade temperature is maintained between the fluid, working fluid, and the surrounding environment. So here it is minus 10, 0 degrees centigrade, here it is outside is 40 degrees centigrade. Now the cycle will analyze Rest of the analysis is simple. Whatever I have taught you regarding the this vapor compression refrigeration system, it is easy to draw because it is saturation cycle. So, inlet of the compressor will be a saturated vapor, then 2, 3 and 4. But here the temperature limits are to be decided by the ambient temperatures. Now, second thing in this numerical is we can compressor power we can always find out because mass flow rate is equal to H1 minus H4, right, and tonnage is required 15 ton. So, this is H1, sorry, mass flow rate is not H1 by H4. Mass flow rate is tonnage is already given 15 tons of refrigeration. So, it is going to be H1 minus H4. So, H1 minus H4, H value of H1 and H4 straight away you can take from pH diagram. Work of compressor you can take, work is H1 minus H4, mass flow rate H1 minus H2 minus H1 will give the work of the compressor. Now, the third one is dimensions of compressor. Now, we assume here it is a single acting single cylinder compressor. So, for this we will have to find specific volume that we can take directly from the pH diagram, specific volume at state 1, right, multiplied by mass flow rate, right. This is the total volume which has to be discharged. Now, this volume is going to be equal to swept volume of the compressor. This is the diameter of the compressor piston or the compressor cylinder. L is the length of the stroke, number of strokes per second, here 750 RPM or N 750, okay, N divided by per second, so 60. So, this much of volume will be handled by the compressor multiplied by volumetric efficiency. Now, here L by D is also, this is a square cylinder, so L by D is 1. So, from these two equations you can, because m dot is already with you, Vs1 you can take from here, N is given, efficiency is given, you can find the length L by D for the compressor. So, that is one typical example. Another is regarding the air conditioning of the system. Now, air conditioning, two things are given, dBT is equal to 25 degree centigrade and specific humidity is equal to 13 grams per kg of dry air, and we have to find all this. Now, from here we can take specific humidity as 0.622 partial pressure of water vapor divided by total pressure minus partial pressure of water vapor. Now, W is 13 grams per kg dry air. So, 13 divided by 1000 is equal to 0.622 PV. Atmospheric pressure is 101.3. So, 101.3 minus PV, and this will give us the value of PV. This can do by yourself, right. From here we will get the value of partial pressure of vapor. Now, this partial pressure of vapor is first is already attained, relative humidity. Relative humidity is partial pressure of vapor when it is saturated at, let us say, 25 degree centigrade dBT. So, this we can take from the properties of steam. You just take the steam table, and from steam table partial pressure of water vapor can be taken at 25 degree centigrade and partial pressure we have calculated from here. These two ratios, the ratio between these two will give the relative humidity. Dew point temperature. Dew point temperature. Now, dew point temperature, when the dew point will arrive? The dew point will arrive when the vapor is completely saturated. A sample of vapor is there which has certain relative humidity. Dew point will arrive when phi is equal to 1. It means PV, this PV becomes the saturation pressure, right. So, we will keep on reducing the temperature. Now, dBT will keep on reducing, dBT will keep on reducing, and when the dBT become wet bulb temperature, and this is equal to dew point temperature. So, we will keep on reducing the dBT till the value of dBT becomes corresponding to partial pressure of vapor. When the value of dBT becomes or it turns to be corresponding to the partial pressure of water vapor, that is the dew point temperature. So, this is how we can calculate the dew point temperature. I can give you one example in addition to this, because normally if you look at the weather data, you will find that dBT is, today dBT is 25 degrees centigrade, temperature is 25, they do not say dBT, temperature is 25 and relative humidity is 50%, right. So, if we take this case, temperature 25 degrees centigrade, relativity humidity is 50%. Now, in this case, so relative humidity is partial pressure of water vapor divided by the saturation pressure of water vapor at this dBT. So, if we look at the properties of saturated vapor at 25 degrees centigrade, it is not given here. So, partial pressure of water vapor at 25 degrees centigrade. So, at 24 it is how much? 2.986 kilopascal, and 26 degrees centigrade it is 3.364 kilopascal. So, 25 degrees centigrade it is going to be 2.986 plus 3.364 divided by 2, 3.175 kilopascal. Now, relative humidity is 50%, so 0.5 is equal to PV divided by 3.175. And if you want to find the PV at this temperature, that is going to be, PV is 1.587 kilopascal. Now, we will find, in order to find the dew point temperature for this air, for this state of air, we will find temperature which is saturation temperature corresponding to this PV. So, 1.587 will be close to 14, it will be between 12 and 14, 1.58, yes, it will be between 12 to 14 degrees centigrade. So, this will be, this temperature we can attain by doing linear interpretation of the values between 12 and 14 degrees centigrade. I think it is going to be close to 13 degrees centigrade at 1.403 plus 1.599, 1.501 is slightly higher than 13 degrees centigrade. Anyway, it is going to be between 12 and 14 degrees centigrade. In order to find the exact temperature, linear interpretation can be done. Now, after this psychometric numerical, we can take another part of this psychometry, that is heating systems. Now, this numerical, this problem involves a heating system. An air conditioning plant has to be designed for a small office room for winter air conditioning. So far we have discussed summer air conditioning, we have analyzed we have done the numericals on summer air conditioning. This is for winter air conditioning. Outdoor is 10 degree centigrade and 8 degree centigrade well bulb temperature. Indoor is 20%, 20 degree centigrade and 60% RH. So, here in this case, if we take the outdoor conditions that are 10 degree centigrade dry bulb temperature. So, this is 10 degree centigrade dry bulb temperature and this is constant dry bulb temperature line, and 8 degree centigrade wet bulb temperature. So, 5, 6, 7, 8. So, this is the wet bulb temperature and we will follow this line. This is the outside air condition. If we show this on psychometric chart, it is something like this. This is wet bulb temperature 8 degree centigrade and this is dry bulb temperature 10 degree centigrade. This is the state. This is a state, let us say 1. Now, indoor condition is 20 degree centigrade dry bulb temperature. Now, 20 dry bulb temperature, 60% RH. So, 50% and 60%. This is the indoor condition. And here we can show indoor condition somewhere here. And this is 20, state 2 is 20%, 20 degree centigrade dry bulb temperature and 60% relative humidity, right. Now, heating and humidification, there are two processes involved here. First of all, we have to heat the air and then humidification has to be done. Now, for heating air and humidification, first of all, we will draw a straight line here, straight line, and then we will draw a straight line, constant bulb temperature straight line passing through this point, and that will give us the supply temperature. So, we will follow this process from 1 to, this is 2, this is 3. So, we will come 1 to 3 and from 3 after heating evaporative cooling will be done. So, in actual arrangement in the duct there is going to be a heater and after the heater there is a spray of water. So, heating and humidification is being carried out. So, here also we can show that heating and humidification, this is state 3. Now, after this it is written bypass factor is 0.2. Bypass factor means there is another state 4 we have to identify, and T4 minus T3 bypass factor, if we consider bypass factor, then bypass factor is, this is 4, T4 minus T3 divided by T4 minus T1, maximum divided by difference. So, sorry, difference divided by maximum. So, this is how we will get the temperature T4. So, now for this temperature, this is 26 degree centigrade. So, T3 is 26 degree centigrade, 26 degree centigrade. If bypass factor is 0.2, so 0.2 is equal to T4 minus 26 degree centigrade divided by T4 is T4 minus 10 degree centigrade, and from here we will get the value of T4, that is the coil temperature. And capacity of humidifier, yes, this is a new term, capacity of humidifier. Capacity of the humidifier is how much water has been added by the humidifier per kg of air. Now, water added by the humidifier per kg of air we can take from here. It is from inside condition, it is a 9, and for this is 9 grams per kg, and from outside condition it was 6. So, 6 to 9, so 3 grams per kg of air water has been added. Effectiveness of evaporative cooler can be taken, there are two things. One is capacity of humidifier, another is effectiveness of evaporative cooler. Now, effectiveness of evaporative cooler will be if you move along, if this is evaporative cooler. So, if you move along this line 15 degree centigrade. So, if we were able to achieve 15 degree centigrade, the effectiveness would have been 100%. So, it is 20 minus, sorry, 26 minus 20. So, the effectiveness of evaporative cooler is going to be 26 minus 20 minus 20, 26 minus 20 divided by 26 minus 15. Actual divided by maximum possible. This is actual temperature drop divided by maximum possible temperature drop. Or in case of humidity also you can calculate actual humidity rise in the case of when the air is totally saturated, that is known as effectiveness of air washer. Now here it is capacity of humidifier, that is expressed in terms of how much water is added into the air. So this water addition in the air, now how much air is circulated? Free air is 5 liters second per person. 5 liters per second per person. So how many persons? 100 persons. So 100 persons, 5 liters per second means the air's flow rate has to be 500 liters per second. So air flow rate is 500 liters per second. Now this liter per second means 0.5 meter cube per second. Now supply air is coming from here. We can take the volume is 0.81 meter cube per second. So, meter cube per kg. So divided by 0.81 give us the mass flow rate of air, that will be in kg per second. This is how, once we have the mass flow rate of air, we can find the total capacity of, absolute capacity of humidifier. So per kg it is 3 grams, then it will be multiplied by the mass flow rate of the air, then we will get total capacity of the humidifier. So likewise, we can also calculate the heating capacity of heating coil as well. Now this was the last lecture of this course. I have completed this course, all the lectures of this course. I hope you enjoyed and learned from these lectures. You can keep on doing practice with a number of books are available on refrigeration and air conditioning in the market. In those books, you will find a variety of numericals. So more you practice, more you learn. So you practice with those books. So keep on doing practice from these books. Soon your examination will be conducted for this course. I wish best of your luck for this examination. Thank you very much for attending this course.